Yeah, I was just saying it's interesting to study black holes because we're having growing experimental evidence that they actually exist. And I'm interested in black hole solutions in modified gravity theories.
Can you speak louder, please? It's still not heard properly.
What did he say? The sound is still not good? Yes. I have to like to hold it here.
Looks like you are not speaking to the microphone, like microphone is far away. Sometimes it is nearby, but sometimes it is far away.
Like this, it's okay?
Yes.
Okay, no, so I have to do like, okay. I have to hold it close, I guess. Okay, no, but I'll just hold it close. Hopefully like this, it's okay. Right, so hopefully the sound is good. I was saying, in general relativity, rotating black holes are described by the Kerr metric. And it's interesting to construct alternatives to this space-time in order to both test general relativity and potentially find signatures of modified gravity theories. And what's usually done in the literature, like in these papers that I list here, for instance, is people usually add some ad hoc deformations of the Kerr metric that could generate some effects that they're looking for and signatures of modifications of gravity, for instance. And what we tried, and what I'll present in this talk, is using the Disformal map, which I'll go into more detail in the following. We constructed black hole solutions in modified gravity, which are actually solutions to some higher order scalar tensor theories. And we believe that this is a nice feature because, well.
Can you hear me?
I'll just continue with this one. It's fine. Okay. And so let me just briefly remind you the framework. I think Evgeny mentioned this, but basically in 4 dimensions, there's a theorem by Lovelock that says that if you have only one metric tensor and include up to its second derivatives, the Einstein field equations are unique. So you can't really get new physics. And in order to change the Einstein equations, you have to either add dimensions or fields. And the simplest way to do this is to add a scalar field. And this leads to scalar tensor theories, which have been developed and enhanced throughout the years, from the Jordan-Brans-Dicke theory to Horndeski, beyond Horndeski, and today the so-called DOST, degenerate higher order scalar tensor theories. Even though the Lagrangian that I write here contains, leads to higher order field equations, by imposing certain degeneracy conditions on the kinetic matrix, it's possible to obtain a theory that doesn't propagate an extra unhealthy degree of freedom called the Ostrogradsky ghost. So this is the general framework of theories that I'll be working with. So I'll start by reminding properties of the Kerr metric in general relativity. And then I'll actually describe what we did to construct this deformation of the Kerr metric. And if I have time at the end, I'll briefly mention some experimental signatures, but I'll focus mainly on the second part about the disformed metric. Right. So you may all know, but I'll try to remind the main features. So in general relativity, rotating black holes are described by the Kerr metric, which I write here, which is a vacuum solution, meaning that the Ricci tensor vanishes. And it's a rotating generalization of the Schwarzschild metric. So in this space-time, you have m, which is just the usual mass of the black hole. And the parameter a is the angular momentum per unit mass, so sometimes called the spin. And you see that there's an important term here, dt d phi, which comes in with this factor a. And the non-vanishing of this term actually signals that the object is rotating. So, right, and when you put a to 0, of course, you recover the Schwarzschild metric, okay? And here I've introduced just some usual functions to make the notation a bit lighter. It's important to note that the Kerr metric has one, like in the Schwarzschild case, you may wonder what happens when delta here goes to 0, right? When in the Schwarzschild case, this is when r equals 2m. And you know that this is only a coordinate singularity in the Schwarzschild case, and it's not actually a curvature singularity. And actually, a similar thing happens for Kerr. And if you calculate curvature invariant, for instance, this is the Kretschmann scalar, you can see that it only diverges at rho equals 0. So rho is this function here. And this leads to the so-called ring singularity of the Kerr spacetime. And you can check that this is indeed the only singularity by performing a suitable coordinate transformation where this is clearly the only singularity. And you can eliminate the coordinate singularity at this delta equals 0. Okay, just like in Schwarzschild, basically. Right. So the Kerr metric has symmetries. So it's a stationary and axisymmetric spacetime. And there are two killing directions, which correspond to this. So the vectors dt and d phi are killing directions. Or said differently, the metric doesn't depend on these two coordinates, right? But moreover, there's an additional symmetry that we sometimes take for granted, which is called circularity. And it basically means that in the Kerr line element here, if you simultaneously flip time and the phi coordinate, the metric remains invariant. Okay, so there's this reflection, which is the symmetry of the metric. And in terms of well, relations, this can be expressed this way. So if you take the one form associated to the killing field dt here and the one associated to d phi, you can calculate this wedge product. And if both of these conditions are satisfied, you say that your spacetime is circular. And another very interesting thing about the Kerr spacetime is that it emits a non-trivial killing tensor on top of the two killing vectors, right? And I say non-trivial killing tensor because so a killing tensor has to verify this generalization of the killing equation. And if you take the Levi-Civita connection, of course, the metric itself is trivially a killing tensor, all right? But for the Kerr metric, there exists another tensor, which also verifies this, this equation. And this actually leads to constant of motion along geodesics. Okay, so whenever you have a killing vector or a killing tensor, and you have a geodesic vector, you can contract this vector with either the killing vector or tensor, and you have a conserved quantity along geodesics. So if you count, right, I just said the metric is a killing tensor, and actually the conserved quantity in this case is the mass of the particle. You have two killing vectors here plus a killing tensor. So in the end, you have four conserved quantities that are all independent, and this allows you to actually write the geodesic system of equations as a first order system. And this was actually found a bit in reverse. So Carter first found that the Hamilton-Jacobi equation for geodesics is separable. So he first found that we could actually separate the geodesic equation. And then the link to the existence of a non-trivial killing tensor was made a few years later. But this is basically what it is. You have four constants of motion, and hence the study of geodesics is much simpler.
Tim, I have a question.
Yes.
Can I ask a question? It's not clear to me why the reflection symmetry is equivalent to these wedge products, that they should be zero. First of all, they're equivalent, right? The one means the other, and the reflection symmetry means that wedge products mean equal to zero, right?
Yeah, this is the definition of circularity.
So yeah, can you shortly comment why? Because I'm lost a bit. Yeah, one symmetry is a reflection of the coordinate, discrete transformation, and the other is just some constraint on the killing vectors. I don't see relation.
Why? Okay. Okay. Well, first of all, this. Yeah, if these two relations are satisfied, it tells you that there exists a coordinate system that actually exhibits this symmetry, but it's not so clear. Like for instance, the Kerr metric, the way it was originally written, doesn't satisfy this reflection symmetry, right? In terms of so-called advanced Eddington-Finkelstein coordinates, you can't immediately see that this is the case. But later, Bohren-Lindquist wrote another, wrote the Kerr metric in another way, which clearly exhibits this symmetry. I'm not sure exactly, like, yeah, I don't know mathematically how this immediately transforms to this wedge product forms. Yeah, this I don't know.
Okay.
but
But from the killing vectors, you can derive the reflection symmetry, right?
Sorry, for killing vectors, I can
From these two relations with scaling vectors, you can derive the reflection symmetry in certain frame.
Yeah, if you can. So of course, this is all for axisymmetric stationary spacetime. So you're sure you have the two killing vectors, and if you construct these two quantities and they're zero, then you're sure there is some coordinate choice where you can have this symmetry. Yeah. And for instance, for Kerr, it's the Boyer-Lindquist, among others, but Boyer-Lindquist coordinates where you minimize the number of off-diagonal components, basically. And the only off-diagonal one is this T phi, which trivially satisfies this reflection, basically. Yeah.
Okay, thank you.
By the way, just a stupid question. What is d psi? How do you act with theorem on vector field? Because psi is vector field, right?
Yeah, sorry.
So it's coordinate dependent or what?
No, sorry. Here I have a shortcut that I should have written. I think I write it later. But what I call it the same thing here, but this is actually, can I write on the blackboard? Do you see if, no, you don't. It's the one form associated to the vector. So it's like g t mu dx mu, basically. Right?
Yep.
I agree. This is when I write this, I don't think of the vector field. I think of the one form. So this is
you put all indices down. Okay, that's clear. So
gt mu dx mu, and this is g phi mu dx mu. Sorry, I agree. This is a shortcut. Yeah. And so of course, then when you act on this, it's just the usual thing on the one form. I agree. It's not completely exact. Sorry. I think I mean later on when I talk about the disformed metric, I think I write it explicitly. I forgot to mention it here. Yeah, anyway, just to say that for the Kerr metric, also Kerr-Newman, when the black hole is charged, you can study geodesics very simply in some sense, because you're left with algebraic equations or first order system instead of, a couple of second order equations. Right, and if you're in the Kerr metric, you can exhibit certain important hypersurfaces of this spacetime. So let me briefly remind this. So let's consider stationary observers, which lie at constant r and theta in the usual Boyer-Lindquist coordinates that I wrote earlier. So let's consider some observer with some time component and also some rotation along the phi direction. Okay, and if you ask for this observer to be time-like, so you want the norm squared to be negative. Sorry, yeah. You basically need to impose some bounds on this function omega, right? And for the Kerr spacetime, you can see it from here. There's a certain surface called the ergosphere, or the static limit, where the time-like killing vector becomes space-like. So the time generator dt becomes space-like. And inside this ergosphere, you have to have both roots of this equation here that are positive, meaning that from the point of view of an observer at infinity, if a time-like observer crosses the ergosphere, this observer has to have a non-zero angular momentum, okay, as seen from infinity. So basically, you're kind of dragged with in the sense of the rotation of the black hole. And this is the radius of the ergosphere. So it's a theta-dependent surface. And if you go deeper now inside the space-time, there's actually a moment where these observers cease to exist completely. So it's when this square root argument becomes negative. And you're left with solving this equation here. And it gives you actually two roots at constant r, which are called the event horizons of the Kerr metric. And the outermost one is called the outer horizon. And okay, so if you cross this event horizon, as in the Schwarzschild case, you can't come out, at least in the same universe. Or, I mean, yeah, you can't come out. So yeah, this is just a plot sort of summarizing this. Whenever you cross the ergosphere, you have to rotate in the positive direction. for stationary observers. And static observers, so who also want to stay at phi equals constant, so just evolve in time, can no longer exist inside the ergosphere. Okay. And another interesting property of this Kerr solution is that the event horizon that we just discussed is actually a killing horizon, meaning that there exists a killing field, which is normal to the horizon and null on it. And it's exactly this killing field right here. And this component here, proportional to d phi, is sometimes interpreted, as some angular velocity of the horizon. And using this killing field, this is how you actually can define surface gravity of the killing horizon. There are many equivalent definitions in GR, but this is one way to just look at the infinity of this vector field K. And then this surface gravity is just related to the Hawking temperature. So you have this very, very nice structure in Kerr that the event horizon is also a killing horizon. Okay, and so this is just a summary of Kerr, basically. So if you come in from infinity, you have this red surface, which is the ergo surface or static limit, and this red region is in between the ergo surface and the event horizon. And then I didn't discuss, but you probably know you have the analog also. So you have an inner horizon and an inner ergo surface, and in the end you reach the ring singularity here in the middle. But of course, the only relevant surfaces really are the outer event horizon, because we don't really know what happens inside anyway. So, right. So this was just a brief summary of general relativity black holes. And now I'll explain what we did starting from that. So I remind just the basic Lagrangian, just to put into context the theories I'm working with again. So we start with what's called a stealth solution in modified gravity, which was constructed a few years ago. And a stealth solution is, so here you have the metric field and the scalar field. Okay, it's a scalar tensor theory. And it's called stealth because there is a solution where the metric itself is exactly the same metric as GR. So basically, there is a non-trivial scalar field on top of the solution, but it doesn't modify the GR metric. So the scalar field doesn't really have a direct influence, but it's there and it's non-trivial. And so they built this non-trivial solution where the scalar field itself is actually the Hamilton-Jacobi potential of the Kerr spacetime. And so they found a solution here with the scalar field. Since it's the Hamilton-Jacobi potential, it's a geodesic direction, and you can see this is clear because the kinetic term of the scalar field here is a constant. So when you calculate this, and you expand it, you can actually commute the two derivatives, the two covariant derivatives on a scalar field. And so in the end, you end up with a geodesic equation here for the vector field nabla phi, okay? So this vector nabla phi is actually a geodesic direction of this solution. And we're gonna use this in the following. So I have to mention that in scalar tensor theories, you're allowed to do what's called a disformal transformation, which I wrote here. Okay, so you may be used to this conformal factor here. This is called the conformal transformation. Of course, all of you know this. And you can add what's called a disformal term here. So this was first introduced by Bekenstein in the 90s. And people have actually showed that there is a class of scalar tensor theories here that is called the 1A class. So it's on the left part of this plot. And you can, if you start with a theory which is inside that class, you can perform this field redefinition of the metric, and you end up with another theory which is also in the class. Okay, so it's stable under the disformal map.
Excuse me, can I ask a question about the previous transparency? Hello? Can I ask a question about previous transparency, previous slide?
Yes.
So the derivative of phi is the killing vector for this solution, right? What happens at the killing horizon? Does it mean the strong coupling for this field, like vanishing of the kinetic term in the Lagrangian?
Why is it a killing vector?
Yeah, I think that I thought that you were pointing out that d mu phi is a killing vector for this.
No, it's a geodesic direction.
Geodesic direction. So it doesn't correspond to any killing vector.
No, but I mean, if you look from here, if you just
so
take derivatives, you have some also r. You have a function of r and
thank
theta, which are not killing.
So you have found some family of geodesics, and that's how you have obtained this solution. That was the point.
Yeah, basically the Hamilton-Jacobi method is used to find the geodesics. So here they kind of associated the scalar field itself to the Hamilton-Jacobi potential. And this is how they found the solutions.
Thank you.
Yeah. And there's some, for their solution to work, there are some constraints on these Lagrangian functions here, but I didn't really go into it. But this is basically how they did it.
Okay, thank you.
Yeah. So yeah, I was saying this 1A class is stable under the disformal map. And what's important to note that, yeah, every time we give a talk about this, people are usually confused, but it seems like we're just redefining the metric. So it's true, it's just a field redefinition, but it doesn't mean we end up with exactly the same theory at the end, okay? Because say you start with a gravitational action here as tilde, depending on this metric G tilde, and you couple matter fields minimally to this metric G tilde, okay? And then you perform the disformal transformation. So as I said, you're gonna end up with another action of the dosed 1A class, but now expressed in terms of this new metric G. But if you wanted the exact same theory, then the matter fields would not be minimally coupled to this new metric G, because if you just replace here on the left-hand side, you would have to have a non-minimal coupling here. You have to replace this G by this whole thing, right? So the theories are exactly equivalent if here, when I go from left to right, if I had coupled these matter fields here to the full expression. But you basically change the gravitational sector, and then in the end, you decide to couple matter fields minimally to this new metric, right? Just G without tildes. And so this is how you obtain different theories. Otherwise, it would just be some invertible field redefinition, and you wouldn't change the physics at all. But yeah, I repeat, here, since it's only G and not CG plus D and this term, it's really a different theory. Right. So since this dosed 1A class is invariant under, sorry, not invariant, stable under the disformal map, this was the idea, was to start with this stealth Kerr solution of higher order gravity, right, which I wrote here. And for some regularity conditions, which I won't delve into, we kill the phi and theta dependencies here. Okay, so we end up with a scalar which depends on T and R only. And we start with the Kerr metric here, GK, and we disform it with a constant disformal factor here. Okay, and this is just rescaling for convenience, but basically this whole thing minus d over q squared is a constant. And what we end up with in the end, what we call the disformed Kerr metric, after also some rescaling of coordinates, is this, okay? And in orange, I wrote what's different from the Kerr metric. So you have some factors of d everywhere, kind of. But also this whole term dtdr, as I'll explain in the following, it's very important because I'll show that we're not able to remove it. I mean, having a dtdr term is not the end of the world. You can think of even the Schwarzschild metric written in Eddington-Finkelstein coordinates, for instance. You have this, in terms of advanced coordinates, you have this dvdr term. So these cross terms are not a problem, but in the Schwarzschild case, you can always eliminate it and rediagonalize your metric, right? But here we'll have a problem because of this term, or an interesting feature, I don't know, but a difference from Kerr, definitely, and I'll explain more in the following. So here delta and rho are the same as for Kerr, right? So delta marks the location of event horizons for the Kerr metric, and this is just a new radius function. So one important thing to note is that when A is 0 in this spacetime, one can actually in that case, write the metric as a Schwarzschild metric with a redefined mass, okay? So our whole procedure doesn't give anything interesting if we start with a Schwarzschild solution. So it's really a feature of rotating black holes. So we'll keep A non-zero in the following. So let me start by saying that the solution is regular. So we can, first to get hints that it's regular, we can calculate some curvature invariance. Of course, it's never enough to calculate as many curvature invariants as you want, but it kind of gives you a hint that if there's a problem, then it'll appear in some curvature invariant. So you can calculate Ricci tensor, for instance, and you see that it's non-zero. So the first thing that this tells you is that the solution is not Ricci-flat. This is the first main difference with the Kerr metric. And you can actually change coordinates, like I wrote here, to coordinates where the only singularity is actually at rho equals 0. So just like Kerr. So basically our procedure doesn't introduce new singularities. So that's a good thing. And in these coordinates that I wrote, the metric components and the scalar are regular in some region, of course, like are positive, for instance. Another interesting feature is that this scalar phi, which is very important in our construction, can actually serve as what's called a global time or cosmic time function. So in the Kerr spacetime, when you have a super extremal spacetime, for instance, so when the black hole is rotating faster than the mass, you can have closed time-like curves, which of course we want to avoid in our spacetimes. But there's a theorem by, so I think it's by Hawking first, but it's in the Wald book also in the Hawking-Ellis, that you can have what's called stable causality if you have a function f, which is a future-directed or past-directed time-like vector field. And actually in our construction, the scalar field phi itself just verifies this property very nicely. So this tells us that we won't have some causal pathologies, like it's very often the case in these ad hoc deformations of Kerr that I was mentioning in the introduction. In many of these cases, you end up with singular solutions or closed time-like curves and things like that. So this is a very nice feature of our construction. Now, a very important property, which I kind of hinted on a few slides ago, is, okay, we still have axisymmetry. You may remember the line element still doesn't depend on time and phi. So we still have the two vector fields dt and d phi. However, now when we calculate this wedge product, so by the way, this is to answer the previous question, okay? What I call this one form is actually just this contraction with the metric. So now when you calculate this wedge product, you actually find that it's non-zero, meaning that the spacetime is non-circular, except of course in the case where d equals 0, where we just have the Kerr metric, and when a is 0, because as I just mentioned, if a is 0, we just have the Schwarzschild metric, okay, which is a subcase of Kerr, so we also need to be circular. But in the general case, the metric is non-circular, meaning we will never be able to find some coordinate system where we have this reflection symmetry. And this actually has a deep impact on the separability structure of the spacetime. There are some old articles from the 80s, 70s, 80s here that show that if you assume a suitable separability structure of your spacetime, you actually end up with a coordinate system that is circular, with a metric that is circular, sorry. So this basically tells us that we have no non-trivial killing tensor for our spacetime, meaning that the study of geodesics is going to be much more difficult than for Kerr. And this feature is interesting because such non-circular spacetimes can actually exist in GR. For instance, when you have meridianal flow of matter. And in the context of modified gravity for numerical simulations, it was shown that the circular ansatz sometimes fails. So it seems that this circularity is taken for granted basically all the time, but it's not necessarily a feature of black holes in modified gravity. Right, so now let me kind of do a parallel analysis to what I did for Kerr at the beginning, okay? So let me start at infinity. And if I start very far away, basically what we find is that the disformed metric is very similar to Kerr. So if you look at it from very far away, you can identify a physical mass and spin of the black hole just by comparing to an asymptotic expansion of the Kerr metric, which I wrote here. All right. So when you do this for Kerr, you find the mass here in the TT component and the spin at leading order in the DT d phi term. So if you do this here, you just see that it's basically Kerr from far away. Now, if we do the same thing with the stationary observers again, so let's take this for velocity here and ask for it to be time-like. So at the beginning, it's the same as Kerr. We have this static limit or ergosurface where the time-like killing field becomes space-like, and inside which static observers are no longer allowed. So this is pretty much the same feature as Kerr. However, these stationary observers no longer exist when this square root argument becomes negative, and this is given by this quantity. So this function that I called P, you have to solve the roots of this equation, and you end up with a theta-dependent profile. If there are solutions, you take the outermost surface, and it gives you this so-called stationary limit, inside which stationary time-like observers, I should say, can no longer exist, right? So if you just kill this term when d is 0, you just end up solving the horizon equation for Kerr. Okay, so this is what I described earlier. For Kerr, you have the ergosphere, and then when stationary observers no longer exist, you actually end up on the event horizon. The thing is, now we have this. And in the general case, if you take the normal vector to this surface, okay, so say you solve this equation and you call the outermost surface r equals r0 of theta, okay? And you have this surface, you take the normal vector and calculate the norm, and you find that the surface is actually a time-like surface, meaning you can cross it in both directions. And importantly, it means that it can't be an event horizon, okay? Because we need a null surface for that. And another interesting feature is that inside this stationary limit, all the killing fields of this form with constant omega are going to be space-like, meaning that even if we delve deeper and find an event horizon in the interior of this stationary limit, it can't be a killing horizon because you need a killing vector to be null on the event horizon for it to be killing. So this is many different features to GR. So the question is, can we find an event horizon inside the stationary limit? So as I mentioned, we need to find a null surface, okay? And what what's usually done in the literature is you expect to find the horizon at a constant radius r in these spherically symmetric coordinates. Sorry, spherical coordinates. And if you ask for a surface to be located at constant r, then what you do is you take a normal vector with covariant components which are just 0, 1. So you don't have this part, okay? If r prime is 0, then it means you're looking at the normal vector to a constant r surface. And if you ask for this norm to be 0, then usually you solve this equation, grr equals 0, and for the Kerr case, you end up with delta equals 0, all right? The problem is in our case, if we solve this equals 0, we end up with theta-dependent profiles, and this violates the original hypothesis, right? Because solving grr upstairs equals 0 means that you started with the assumption that in the end you'd end up with a constant r surface. And this is actually a mistake that's done often in the literature. I mean, I've seen a few papers where they do this. They just think that to find the event horizon, you have to solve this equation. But this is only true if in the end you actually get constant r solutions. So in our case, we don't. So you have to consider more general profiles like this, so theta-dependent surfaces. And a necessary condition for this surface to be null, to be an event horizon, is for this vector, this normal vector, to be null, right? So if you take this and write n squared equals 0, you end up with this equation. So instead of just p equals 0, which is what people do following this naive assumption, you actually have to introduce this derivative, okay? Sorry, I didn't say, but a prime is derivative with respect to the argument. So derivative with respect to theta. And so in the end, you end up with this equation, which is not easy to solve. I mean, analytically, you can't solve it. And just to say it once more, if you take the Kerr example, you don't have to consider this theta dependence, d is 0, and you do get constant r solutions, which give you the Kerr horizon. But in our case, you don't, because solving this piece gives you theta dependent profile. And also something I must add is that to have a smooth solution, you have to impose that the derivatives at the poles in the equator are 0. And okay, using these, if you want to have a smooth solution, I'll just go quickly, you have to have an upper bound on the rotation parameter. So you can't have a smooth solution all the time. You have to, for a given disformal parameter, you can only have some maximum rotation. And this was all, sorry, I said we can't solve it analytically, so we just solved the profile numerically, basically. Now the question is this surface, because, okay, solving this null normal vector condition is a necessary condition to have an event horizon, but it doesn't mean that if you have a null surface, it's necessarily an event horizon. So what we calculated to kind of convince ourselves that it is an event horizon is an analogy with what's sometimes done in GR. What you do for Kerr, for instance, is you look at the family of hypersurfaces given by the location of the outer event horizon plus some shift. And you show that the surfaces are all Timelike for this data positive. And then for some region inside the outer event horizon, these surfaces become space-like. So you can foliate space-time with the null surface, which is your event horizon. If you go outside, it's Timelike, and a little bit inside, it's space-like. And so we calculated this for our space-time. So this is the horizon profile that is solved numerically. And we shift it a little bit and check that it's Timelike for positive theta. And if theta is negative, we check that it's space-like a little bit inside. So this is, I mean, what we did to convince ourselves. So we call it an event horizon, but it's not like 100% that this is right. We're still thinking about it a little bit. But I will call it an event horizon.
What's the definition
of event horizon? So it's, well, it means that you can't be, I mean, in contact with the inside, basically. I mean, there's a topological definition, but as you can see, I'm not really doing topology. It's defined as the boundary of, okay, now I don't have it in mind, but there's some, basically the boundary of, so if you take the lights, the signals that can reach scribe plus, I guess, like, so asymptotic infinity. Yeah, I guess you end up with, okay, I'm sorry. Yeah, I don't remember the exact definition, but it's given in terms of topological terms. Or you also have this notion of trapped surfaces, basically, where, I mean, nothing can escape from it, basically. You have to show this. But if you...
I don't, to me, the fact that it's now already means that
yeah.
cannot escape from like underneath.
Yeah, this is also like the intuition I have, but I don't think it's enough. I don't think every null surface is an event horizon. I think there's like some subtleties that I mean, I admit I don't really understand completely, but this is why I'm saying I'm being careful. I mean, as I said, many people call this event horizon by solving this kind of thing, which is clearly wrong. So I agree it's maybe some sort of liberty to call it an event horizon. This gives you a hint that it might be actually an event horizon, but it's actually very complicated. You also have the notion of like apparent horizons and things like that, which, yeah, I admit I don't know the full, this is like what I'm trying to understand, kind of. But anyway, I'll call it an event horizon because it's a null surface. And this is just a summary of the space-time structure of this disformed Kerr metric, okay?
I have a question. Did you find some geodesics, like, for example, light geodesics in this geometry?
So no, I mean, there was a paper from some Chinese group, I think, a few months after we published this about, yeah, they were doing like some shadows of these black holes. So they were studying some light geodesics. But as I said, it's the geodesic equation now is very, I mean, it's not separable. So you just don't really know what to do with it.
It just has to do something with horizon, right? Because horizon is defined as a boundary of the past of the future null infinity. So you take
Right.
null infinity, you take geodesics from null infinity, or just some light-like rays, and
Yeah.
the space-time, the span is the outside of the black hole. So
Right. Yeah, yeah. Okay, I see what you mean. But no, we don't have these either.
oh,
Yeah,
okay.
yeah. That would be. I guess that would be one way to convince yourself that this is indeed an event horizon. No, I see what you mean. No, we don't have it. So yeah, as I was saying, as in the Kerr case, this red region is the ergosurface, but here you have, what I didn't mention is that this stationary limit is very, very close actually to this null surface in black. So you have the, what I'll call the event horizon in black, and it touches at the poles and the equator, this stationary limit. And there's a region in between that, well, it's kind of strange because as I mentioned, all the killing vectors are space-like inside. And it's really a new feature compared to Kerr because, yeah, again, for Kerr, these these green and black surfaces are actually exactly the same. And for Schwarzschild, the three surfaces are the same. So this is one of the main questions that we have, like what happens inside this region? What are the properties? Because it's really a new feature of these spacetimes.
There's no sound again. I'm sorry.
Change sound. Is it good?
Now it's okay.
Okay.
Okay, sorry. Okay, so I'll just repeat. Sorry, the disformal parameter d is bounded by -1 and plus infinity. And so I was saying we're constructing simpler spacetimes in both of these limits. So the first case, d goes to infinity. If one introduces the physical spin here, which is the dimensionless physical spin here, physical spin over physical mass, in an appropriate choice of coordinates, you can write it like this. And so you can see that this spin in orange, when it's 0, you just have the Schwarzschild metric in usual Schwarzschild coordinates, right? But here you have some, you have some dt d phi term. So when you expand this to first order, it's kind of like a lens theory term, for instance. But you see that it comes also with a dr d phi term. And this is where the non-circularity comes from, okay? Because of course, here, if you shift time and phi simultaneously, it's squared, so you don't change it. But here you're going to change to a plus sign, of course. But we expect this because, as I told you earlier, it's impossible to write these metrics in a coordinate system where you can have this simultaneous change. And actually, yeah, let me mention that in this case, it's very easy to use the Newman-Penrose formalism to calculate the Petrov type of these metrics. For this metric, it's very simple because this is almost immediately just you can build a real tetrad immediately, right? Because it has the Minkowski form. And using this real tetrad, you build a complex tetrad, build the Weyl scalars, and you can build these combinations of Weyl scalars, so psi I, which are actually also invariant under the rotation of a tetrad. And what you do with these I and j is you can calculate what's called the speciality index, which is just this ratio. And for algebraically special spacetimes, so anything apart from type 1, Petrov type, this has to be 1. So any algebraically special spacetime has to have s equals 1. And for this metric, which we called non-circular Schwarzschild, you can actually see that when this rotation parameter is non-zero, s is not equal to 1, meaning that this metric is of general Petrov type 1. So you don't have any of the features of Petrov type D, for instance, which is the usual Petrov type in general relativity, black holes. And this is true for the generic disformed metric, even not in this limit, but it's just very easy to calculate in this limit. So this is why I put it on this slide. And another one we constructed is what we call the quasi-Weyl metric in the other limit, d goes to -1. And this is also strange because it doesn't include a dt d phi term. So it basically from infinity, it looks like a non-rotating black hole. But once you zoom, you actually end up with these non-circular properties again. And just to say, what I put in orange here is that usually when you have a dTdr term, at least for spherically symmetric spacetimes, you can always redefine the time coordinate by a function of r to eliminate this, okay? And why this fails now is because of the theta dependence here. So you can't just do a simple shift, dt goes to some new coordinate plus a function of r dr, okay? Because it would be incompatible with your original answers. So basically this theta dependence in the GTT component is why it's, is a key feature of this non-circularity. But anyway, in both cases, we have some simpler examples of these disformed metrics, which may help us to understand some of these properties in the following, in the future. Like non-circularity or this killing horizon thing, And I guess I'll stop. I don't know. Do I have time still, or?
Well, I think you can take like 15 minutes more.
15. Okay. Then I'll do it. Yeah. So then what we. So here I've presented sort of theoretical properties of these spacetimes, but then what we wondered is what happens about with stars that orbit a disformed black hole. So if you keep in mind, as I said in the introduction, that we're starting to have data from this star S2 orbiting Sagittarius A star at the center of our galaxy. And the gravity collaboration has already measured, in some sense, with some uncertainties, of course, the Schwarzschild precession predicted by general relativity. And we wondered what would happen if instead of Sagittarius A star, well, if Sagittarius A star was a disformed black hole and not a Kerr black hole. So this is just a picture of the situation. So you assume in O here, in one of the foci of the red ellipse, you have a disformed black hole, and S here is just a star. And you can describe the orbit with many angles. So here omega is the so-called nodal angle. You have the inclination angle. The pericenter P is located by this lowercase omega. Then you trace the location of your star with this function, this coordinate F. And you can use what's called the oscillating orbit method to trace the secular evolution of these quantities. So over time, how these quantities are going to change. And so as I said, the pericenter precession, so the secular variation of this angle here, has already been measured by the gravity group. And in the future, so either when more data from more stars, notably orbiting closer to the central black hole, will be available, or from binary pulsars. For instance, if we can find some pulsar that has some nice properties near the black hole, we'll be able to measure the angular momentum and quadrupole moments of Sagittarius A star through the measurement of secular variations of this nodal angle and inclination angle. So just basically in the future, we'll be able to measure the spin and quadrupole of Sagittarius A star, and this will allow to test many models of modified gravity. Because in GR, you may have heard of the so-called Nohair theorem, which states that for Kerr black holes, but also for charged black holes, basically it's always determined by a small number of quantities. So for Kerr black hole, if you specify mass and spin, you also specify all the higher order multipoles. And for instance, the quadrupole is just given by minus mass times spin squared. But any higher order multipole, there's going to be no new parameter. So we applied this method to the disformed metric and basically calculated the secular shift of all these parameters which characterize your oscillating orbit, the ellipse. Here, alpha and beta are just a rewriting of eccentricity and pericenter angle. And what we get is actually up to 2pn order, a thing very similar to Kerr. So anything that is not an orange is just the usual Kerr result. But what we do get is anytime the quadrupole moment terms appear, we get a rescaling by 1 plus d. Okay, so here these two terms, for instance, are just the usual Schwarzschild precession, which were measured by the gravity group. Here you get some lens steering terms coming from the dragging of inertial frames, and here you get some quadrupole terms. and the Schwarzschild correction, the higher order correction, sorry, to the Schwarzschild precession. But anytime the quadruple terms appear, you get a rescaling. And what this tells you is that the dimensionless quadruple in the disformal case is actually rescaled by 1 plus d. So it basically violates the Nohair theorem whenever this disformal factor is non-zero. And this means that when in the next years, when the Nohair theorem is going to be tested by measuring the spin and quadruple of Sagittarius A star, it may, I mean, it will definitely be a tool to rule out some of these theories or solutions. And also what we tried is to maximize the effects of disformality by choosing this disformal parameter very close to -1. So not quite at the limit of this limiting metric I presented, but very close to it. And in this case, you can actually change the Schwarzschild precession. So the leading order in the pericenter precession here can actually be modified by these modified gravity terms. And this constitutes a signature of modified gravity and a way to constrain this disformal parameter in the future once the spin here will be measured. So yeah, also what we tried is to see how we can constrain this parameter if we have some more data about another star, because for the moment they only really monitor S2 very, very nicely, because they've been collecting data for more than 25 years and it's done more than one period. But if some more stars are observed, then it can allow also to test these solutions and the disformal parameter. So okay, let me conclude. So we constructed deformations of the Kerr metric in the context of scalar tensor theories of gravity, which have many interesting properties, among which non-circularity, which seems to be the key feature of these new spacetimes. But also, as I discussed, that the horizon is not a constant R surface. We don't know how to solve the horizon equation analytically. It's not a killing horizon, et cetera, et cetera. And the existence of this new type of surface, the stationary limit, which in our case is not the same as the event horizon. And okay, so for the orbit of stars, we calculated some signatures of these spacetimes, which will be able to be tested in the future once we have the spin and quadruple of the black hole. And let me finish by noting that some papers have studied aspects of these solutions. So for instance, the particular scalar tensor theories that these objects solve, but also, as I mentioned, the shadows of the black hole, or more recently, kind of extending what we were saying about stars around the central object. What if you have binary pulsars around Sagittarius A star, and how can you test non-circularity in that case? So thanks for your attention.
Any questions?
Can I ask a question?
Yeah, sure.
Okay. So what about the thermodynamics? Well, other than the nohair, like for example, the temperature of horizon, is it constant across the horizon? Not across, along the horizon.
Yeah, so this is one of the main things that I want to study now. I mean, about this subject. So this all has been kind of on pause for the past months because I was doing my thesis, and now I'm working on things that are not really related to this, but I plan to come back to these issues. And the thermodynamics is the main thing that seems to be interesting. So as I mentioned, this horizon can't be a killing horizon. And there have been some papers where they kind of say what to do for basically surface gravity for non-killing horizons. And what seems to be the problem here is, so as I mentioned, for Kerr, I said this is one of the definitions of surface gravity, but you have like, I think even in Wald's book, you have like at least 5 or something. You have many definitions which coincide, they all coincide in GR, so everything is nice. But when the killing horizon is not, when the the null surface is not a killing horizon, all these definitions now don't coincide. So there is a question as to which definition really gives you the surface gravity. What does it even mean in this case? So suddenly it's not so trivial as in
Not the physical question, right? Physical question is what is the temperature of horizon?
Exactly. Yeah. I don't know. This is what this is the plan to try to see what it means in this case.
Yeah, I mean, you can consider a physical process of Hawking radiation, like quantize some field on the background of this black hole and look what temperature will come out.
Yeah,
okay.
this I didn't try, but I guess it's this is a more practical approach, I guess. Yeah. But it is a real question. I agree, because what happens around this null surface is really different from GR, and we don't understand really.
When you said that something is different from GR, what do you mean by GR? Just pure GR, GR with some else?
Yeah, sorry. Whenever I say GR, it's like Kerr black hole. I mean, in this context, when I say the properties are different from GR, I always have in mind the Kerr example.
So no matter.
No, just like Kerr black hole, yeah, in vacuum.
And what about this theory? Like if you rewrite it kind of like GR plus matter, or you cannot do this. Like whether matter is going to be healthy, like some constraints on energy.
Well, you can always view this. You can always write the Einstein equations as the Einstein tensor plus some energy momentum tensor given by the scalar field. So you can always kind of view the scalar as some matter, yeah. But I don't. What's the question?
Well, I just wonder whether these unusual properties probably are related to the fact that, well, just related to the presence of matter.
Yeah. For instance, the fact that it's not Ricci-flat, this is clearly from the scalar field, yeah, which acts as some kind of matter. Yeah. But it's not clear really how it works, at least not to me.